All right, party people. Got another crazy physics problem for you here. So this one, we're getting a little familiar with vectors and calculus. So what's happening is we are given the equation of the moon going around the Earth. We're given the x and y coordinates at all times. And we're going to be asking a couple questions like what is the velocity, what is the acceleration, etc. All right, so we're told it moves in a circle, and its position in x and y coordinates is given to us. And it equals cosine of t and sine of t. So you can think about this, but what this plots is a circle. At time t equals 0, it's over here. At time pi over 2, it's over here. At time of pi, it's over here, and so on. Makes a circle. So the first thing we want is the velocity vector. The velocity vector is just the first derivative of the position vector. So I'm going to get negative sine of t, comma cosine of t. Okay, easy enough. Part B asks for the acceleration vector, which is the derivative of velocity. So that's going to give us negative cosine of t, comma negative sine of t. Sine. Okay, easy enough again. We're just taking derivatives. When we take a derivative on a vector, we just do it term by term. But remember, that's for x and y coordinates. You don't want to do that for spherical coordinates, polar coordinates. For part C, we're kind of doing that. They ask what is the derivative of the magnitude of the position vector. Now let's think about it, right? My picture is over here. The moon is going around and around in circles. So the magnitude of r of t is the radius of the orbit. That's what the magnitude of r of t means. It's a number. And it's going around in circles. So it should be constant, right? The magnitude of the orbit is constant. So it does not change with time. Therefore, this should equal 0. But why don't we see if we can do it exactly? So if we're taking the derivative of that, that means we got to take the derivative. Let me try and keep the r on screen. So we have to take the derivative of the square root of cosine of t squared plus the sine of t squared. Cosine squared plus sine squared always equals 1. So we're taking the derivative with respect to time of 1. Okay? And of course, derivative of a constant is always 0. So sure enough, we proved that the orbit of the moon is not changing, the orbital radius is not changing with time, at least in the scope of this problem. It does, of course, change in real life.